G'day guys, Jake here from Journey Van Builds. There is a huge difference between having a nice diagram and a theoretical understanding of 12-volt components and actually knowing how to put it all together. In this video, we're going to walk through step by step how to build this super reliable and beginner-friendly 12-volt system that I put in my own vans. We're going to touch on the really key safety aspects as well, like correctly sizing your fuses and cables, so you'll be able to take everything that you learn in this video and apply it to your own build. Let's get stuck into it. Before we jump into the install, here's a quick rundown of the components in this system and what it actually powers. First, we've got two ways of charging the battery so that we never run flat. DC to DC charging from the van's alternator and solar. Both of those go into the 2-in-1 battery charger here from Aranging. So instead of wiring in a DC-DC charger and MPPT, it's all handled in this one unit here. From there, power runs straight into our 100 amp hour lithium battery. From the battery, our power is dispersed throughout the van via our 12-volt fuse block here. You'll also see a few fuses and breakers in this system. I'll get to those in a moment. So in my vans, this system usually powers lighting, a 50-litre fridge, the water pump, USB outlets, as well as 2 fans. I also run a 240-volt outlet for charging my laptop, which means I have an inverter in this system as well. For this video, I've left the inverter out just to keep things simple. That doesn't affect the rest of the design. So whether you would like an inverter in your system or not, you're still able to follow along with this video and then add the inverter at the end if that's what you're after. And if you want to check out any of the components that I've used in this setup, I've linked all of the items in the description for you below to check out later. Now, a little pro tip for you before you start installing your system inside your van, I highly recommend putting all of your components together on a temporary board, just like this one here. This lets you take everything you've been learning for theory in weeks now and actually see it play out in front of you as you start to place your components around the board, which is by far the best way to learn 12-volt systems. It also means that you can confirm that the system you've got actually works. You can test your appliances as you connect them in your van conversion, and you can also play around with the layout and where you're positioning things on the board first. And because your temporary board matches the exact space that you'll have available, you can either transfer everything inside your van when the time comes, or simply mount the whole board into place when you're ready. Now, before we start placing components onto the board, we need to start talking about the first big safety topic of your 12-volt conversion, which is fusing. My first rule with fusing is always check a component's user guide or diagram first. Any decent battery charger or inverter is going to tell you the exact fuse size and where to put it in your system. For the rest of your system, the simple rule of thumb is this: any positive cable coming off of a battery should be fused as close to the battery as possible. You can cross-check that with diagrams like the one I've got linked for you in the description to make sure you're on the right track. So as a rough example for you, this battery charger can push and pull 50 amps. So we take that 50 amps and add a little bit of headroom, about 20%. And that gives us a fuse size in the 60 to 75 amp range for this component, which is exactly what's listed in this component's user guide. Then we make sure that the cable we choose is rated above that again, so that the fuse is the weak link. You can repeat this exact process for every major component within your build, but always make sure that you double check with sizing charts and the manufacturer's recommendations. You might also notice that I am using circuit breakers here instead of fuses. They do the same job in terms of protection, but circuit breakers have the added function of being able to be turned on and off, which is really handy for maintenance or if you're killing the system to put the van into storage for a little while. Fuses are generally a touch safer and faster acting, so a lot of people do choose to use a fuse over a circuit breaker in any high current runs, like from an inverter to your battery, for example. And just a quick reminder, guys, I am not a licensed electrician. This video and my diagrams is just to help you understand ideas and concepts. You should always double check and research your own 12-volt system to make sure that cable sizes and fuses are sized correctly. Alrighty, now that we've got all of our components, our circuit breakers and fuses here, we're ready to start piecing this board together. Now, when it comes to finding the correct layout for your board, there is no one correct way of doing this. There are just a couple of rules of thumb that you should follow. First of all, being that high current runs should be kept as short as possible. One, for safety reasons, the longer a cable is, the more chance it is that it could overheat. And secondly, it's going to save you money buying less of that thicker gauge cable. Other than that, you just want to keep your cable management in mind. Imagine cables running from one component to another, how things are going to flow in a way that you're able to tie all of your cables down nice and neat. But in the end of the day, the correct layout for you is the layout that allows you to fit all of your components in the space that you have provided. So now we've placed all of our components. The obvious thing that's still missing is our cables to make those connections. Now, sizing the cables that you use in your 12-volt electrical system is one of the biggest safety concerns of the whole process. So I'll walk you through now quickly how you can do that, because luckily it is easier than you might think. So all you need to do is get your hands on a cable size chart like this one. I've got this particular chart linked for you down in the video description if you want to follow along. The first step is to find the highest current or amperage that a cable is going to need to carry. Realistically, that is the maximum amperage that a component is able to draw, but in practice, what we want to do is size our cable to be able to hold more than the fuse or circuit breaker we have protecting that line. So if a circuit breaker is 70 amps, like in our previous example, we want our cable to be able to carry a little bit more than 70 amps. Step 2 is to select the critical system column with 3% voltage drop. The column to the left of that, which allows for 10% voltage drop, in really simple terms just means it's allowing for the cables to heat up slightly more in theory. So of course, we want it to be as safe as possible. So always refer to the critical system column with 3% voltage drop. Step 3 is to find the correct cable length range. So in the 3% voltage drop column, find the distance that your cable will need to run. It's important to note that cable length means the total distance of positive and negative cables in that circuit. So on a board like this one, of course, it's all pretty tightly packed together. We're rarely going to venture outside of the 0 to 2 meter range, but it's worth keeping in mind for things like runs to your alternator or to appliances at the back of your van later on. Step 4 is to find the correct cable size at the intersection of those 2 points. Taking the amperage and the distance of your circuit and running down and across the chart to find where they intersect. Reference the conversion chart down the bottom to find what that nomination is in AWG, millimeters squared, or the diameter of the cable. That's really handy to have because stores will label their cables in all different ways, so this conversion is nice and handy. So we're after a 4 AWG cable. You'll notice that the 70 amps is right on the cusp there. You could go to a 6 AWG cable, which can hold 70 amps. But other than costing just a little bit more, there is no downside to having an oversized cable, whereas an undersized cable is the #1 culprit for causing fires in your 12-volt systems. As with everything that we're looking at here today, it's a lot easier once you actually have it in front of you and you start working through these steps practically. You'll start to figure it out, and it's a lot less daunting than you might think it is, trust me. And also, it's really important that you get auto and marine grade cable. There are a few differences with this particular cable, but most importantly is that it is a multi-strand cable, so there are thousands of little strands of wire in there rather than just a few thicker ones. So that's going to help prevent the cables from snapping over time with vibration and so on. And they are also copper or tin copper as well. So in Europe, it's not a problem at all. You can get them on Amazon easily. Here in Australia, I go into JCar for those cables. It's the only quality that I've been happy with so far. Okay, so making our connections between all of our components here, we're going to start between the battery charger and the leisure battery here. To begin, we need to make our first crimp connection on the end of the correctly sized cable, which we've established earlier. Start by holding your terminal lug against the end of the cable and marking exactly where you need to strip the insulation back to, that all of the bare strands can reach the end of your cable lug. To cut smaller gauge cables, you can use your 3-in-1 crimping tool, which I'll demonstrate in a moment. For larger gauge cables like this 4 gauge here, the safest way to do it is with an insulation stripper specifically designed for larger cables, but since you're probably only going to be doing this job once, you can get away with just using a Stanley knife by making lots of tiny cuts around the cable until you're able to pull away the insulation with some leverage. Be careful though, because if you do cut too deep, you will cut through dozens and dozens of these tiny metal strands inside, which reduces the amount of electricity that cable can safely carry. With the insulation cut back, it's time to make a really solid crimp connection.
You do that by carefully placing all of the strands inside the lug. I like to give the strands a gentle little twist just to get them a little bit more uniform, but be aware that if you put too much twist in this, it actually makes the strands thicker and can make it more difficult to slide them into the lug. For smaller gauge cables, again, you'll be using your 3-in-1 crimping tool, where for insulated lugs, you use the same color crimp as the color of the lug's insulation, usually red, blue, and yellow. For thicker gauge cables, I recommend using a hammer lug crimper. They're nice and cheap, but their simple mechanical design allows for rock solid crimp connections at a cheaper price point than other hydraulic crimping tools. To use these, again, place all your strands inside the lug and place the lug in the cradle of the hammer lug crimper. Give it 2 or 3 good hits with a hammer or until you can feel a nice and solid connection as you strike the crimper. A little pull test and you're good to go. Once you've made that connection, you can place the lug onto the terminal where it will eventually go to determine the exact length that you need to cut your cable. Make sure that you're bending and contorting this cable to sit the exact way that you want it to be tied down eventually, so that you can accurately mark where to cut the cable at the next terminal bolt. At this point, it's a matter of repeating the same process on the other end of this cable, stripping back insulation, placing your lug, and making a solid crimp. But before you're ready to place that cable between your two components, you'll need to protect the area between the lug and the insulation with some heat shrink, or you can use a couple of layers of electrical tape too.
Okay, now we know how to make a really solid connection. We're ready to start piecing this all together. So I'll walk you through the order that I do that in. So this is our battery charger running from the positive out terminal to our circuit breaker and ready to go to the battery once we put the battery in place at the very end. The next cable is going to be our negative for our battery charger, which needs to be able to run from the negative out terminal here down to the negative of our battery terminal. I've already sat the battery in place there and sort of sized up all of my cables, cut them to length as I've been going through the process of making my crimp connections. So right now I'm just going to show you the order that we're installing, but I've already correctly cut these lengths of cable.
Next, I connect the solar positive from the battery charger to the circuit breaker. This breaker doubles as an on-off switch, so you can isolate the power coming in from the solar panel if you ever need to. For this short run, I'm just using an off-cut of the same solar cable which feeds from the solar panel on the roof down into the van. That's the only solar connection I'm making for now, with the rest being done once the board is mounted inside the van. At that point, the solar positive will run from the solar panel and land on the other side of this breaker, finishing the positive connection, and the solar negative will run straight to the leisure battery's negative terminal. As a quick note as well, if the terminal lugs aren't insulated like the ones you see here, then you just use the non-insulated crimp setting on your 3-in-1 crimp tool and then seal the crimp with your own heat shrink or tape afterwards. The last connection to be made on the battery charger is the alternator positive cable, which runs to the positive terminal on the van's car battery. This is another one that can't be connected fully until we move the board inside the van, but I make the connection with about 2 meters of cable so that I know it will be able to span the distance from the charger into the van's engine bay to connect to the car's starter battery positive terminal when the time comes. That connection is made via a terminal fuse on the positive terminal of the car's starter battery, and a negative cable does run from the leisure battery to the earthing bolt right next to the van's starter battery as well, or alternatively directly to the starter battery's negative terminal. That cable isn't seen in this video because it happens entirely once the board is moved into the van. Back at our board, the next connection we'll make is from the positive terminal on the 12-volt fuse block to its circuit breaker, and then from the circuit breaker to the positive terminal on the leisure battery. Next is the negative terminal on the 12-volt fuse block, which will go directly to the negative terminal on the leisure battery.
And suddenly we're at a very exciting point in the whole process where we are ready now we've done everything that we can, before attaching the battery and then our solar and alternator once we're ready to put this thing in the van. So we'll flick these circuit breakers on and we should see some action on the little lights here. So this is our charger circuit breaker. There we go. They all lit up red there for a moment. And now we've got on the right hand side here, the blue light signifying that this is set to a lithium ion battery, which is perfect. That's what this battery here is. The way that you do that is just with a little small button on the side there. You push that until the correct light comes on that represents the type of battery that you have as your leisure battery. If your car battery in your alternator is obviously a lead acid or a different type of battery, that's not a worry. You need to just set it to the battery type of your leisure battery here. The second light here being yellow is just showing that our battery here is at a normal state of charge. It's not full, so it's not green. It's also not empty, so it isn't red. It's just somewhere in the middle there. And the solar light and the alternator light, they're not on because we don't have any input at the moment. So I'll quickly plug in a solar panel here outside with our extension lead, see if we can get some power coming into the system just to show that it's all working. So there you go, we've got a red light on our solar input. The system's working, it's charging our battery at the moment. This is the point where I would install this temporary board in my van as I'm building, so I'm able to test all my circuits as I go, my lighting circuits, my plumbing, everything like that. And you would also be able to permanently make your connections with your alternator and your solar in. Just be mindful, once you put this in the van, if you're not testing a circuit like your lights or your plumbing, then turn all of your circuit breakers off and leave the system dead while you're not working on it. So you're not working on a live system as you're putting together your van. And just use the fuses that you need to as you are testing your circuits so you don't have unnecessary circuits live. Hopefully you've taken away a heap of insights from this on how to build your own 12-volt setup. If you have any questions about how to apply this to your own van, then fire away in the comments. I'm going to answer every single one of those for you guys to try and give you the confidence to tackle this in your own van conversions. Thanks for watching, guys. I'll catch you on the next one.